Hello mathematicians, thank you for joining me as we look at some of our homework problems from chapter 11 and 12. We'll go through some different things about sets and proving non-conditional statements. As we work through the first problem, what we want to show is we want to show a subset proof, and we want to show that the set of all x and z such that m times n divides x is a subset of the set x and z such that m divides x intersect the set of x and z such that n divides x. So, because we have a subset proof, what we want to do is let A be in my left-hand set. We'll call that A, and we want to show that then A is in my right-hand set, B. So as the case with any subset proof, we let A be an arbitrary element of A. We show it's in B. This means everything in A is also in B, so A is the subset of B. So we're going to continue again by writing down the definition. So what this means is that A is an integer and m times n divides A. And what I want to show is that A is an integer and m divides A, and A is an integer and n divides A. So again, I'm in the intersection of those two sets, so it has to satisfy these properties and these properties. So I have to show it satisfies all of these properties based on it satisfying these properties. Well, notice that we have A as an integer, so we get A as an integer. So what we have to do is we have to prove m divides A and n divides A when mn divides A. So again, we'll continue by definition. A is m times n times k1, and I have to show A is m k2, and A is n k3. And so actually, I kind of already have this because I noticed that, well, A is m times n k1, but n k1 is an integer. So we'll let k2 equal n k1, and we'll let k3 equal mk1. And we'll notice that A is already written as m times k2 and n times k3. So therefore, m divides A and n divides A. Hence, A is an element of B. So A is indeed a subset of B. That is, the left-hand set is a subset of the right-hand set. All right, the next homework problem, we have a set A is equal to set B proof. And to recall that to show A is equal to B, we have to show A is a subset of B and B is a subset of A. So for my proof, I'm going to start off with show A is a subset of B. So let's let A be in A. I have to show that then A is in B. Well, in this case, the A I'm talking about is the right-hand side, so that means A is in the set of all things that look like 9 to the n such that n is a rational number. So what that means is A is equal to 9 to the, let's say, n1, where n1 is rational. In order to be in B, it has to look like A is 3 to the n2 for some n2 and the set of rational numbers. So to be in A, it has to look like this, and to be in B, it has to look like this. So we get to assume it looks like this, and we have to show it looks like this. Now, to get this one out, it just takes a little bit of playing around, but the idea is that I know that 9 is equal to 3 squared. So A is 3 squared to the n1. But if I have an exponent to an exponent, I multiply, so I get 3 to the 2n1. Notice that 2 times n1, since n1 is rational, 2 times it is rational. So we can let n2 equal 2n1. And in that case, we get A is 3 to the n2, because n2 is 2n1. So therefore, if A looks like 9 to the n1, it can be written as 3 to the 2n1, which means it can be written as 3 to the n2 for some rational. Hence, if A is in A is also in B. In order to finish up the equality proof, we now have to show that B is a subset of A. So let's let B be in B, and then we have to show that B is in A. So since it's in B, B is going to look like 3 to the n1, where n1 is rational. And I have to write B as 9 to the n2, where n2 is rational. Now I'm going to use a similar trick to what I had last time, but what I get this time is that b is equal to, well, 3 is actually 9 to the 1/2, because 9 to the 1/2 is the square root of 9 is 3. So 3 to the n1 is 9 to the 1/2 to the n1 is 9 to the, if I multiply these two, because I have an exponent to an exponent, I get n1 divided by 2. However, since n1 is rational, if I divide by 2, I still get a rational number, so I'm going to let n2 equal n1 divided by 2. Then we do indeed have that b is 9 to the n1 over 2, or n2, which is a rational number. Hence, if b is in b, b is in a, so b is a subset of a. Since we've already shown a is a subset of b, this means that b and a are actually the same sets, and they consist of exactly the same elements. Alright, so now what we have is an if and only if proof, and what I want to show is that a is congruent to b mod 10 if and only if a is congruent to b mod 2 and a is congruent to b mod 5. So if you recall, an if and only if is then a proof that we have to do in both directions. We have to do if this, then that, and if the then part, then the if part, and so we have to do both directions. So to start off, I'm going to do a right-hand direction, and my proof is going to be let a be congruent to b mod 10. I have to then show that a is congruent to b mod 2, and a is congruent to b mod 5. Now I know that there are mods in here, so I want to use modular arithmetic, but because I have different numbers after the mod, that makes that difficult to do. So instead what I'm going to do is I'm going to use the definition that, well, a is congruent to b mod 10 if 10 divides b minus a. And I have to show that a is congruent to b mod 2, which means that 2 divides b minus a. And if a is congruent to b mod 5, that's equivalent to 5 divides b minus a. So instead of trying to work with mods in this one, I'm going to work with divisors. And so I'm going to say if 10 divides b minus a, then 2 divides b minus a, and 5 divides b minus a. Well, if 10 divides that, that means b minus a is 10 times k1. And I have to show b minus a is 2k2, and b minus a is 5k3. Well, notice here that, as we've seen in some of our other ones, we can just factor the 10 into a 5 times a 2. And what I get is I can let k2 equal 5k1. Then b minus a is 2 times 5k1, which is k2. And we'll let k3 equal 2k1. Then b minus a is 5k3, which is 2k1. So we get exactly what we're looking for, is that 2 divides b minus a and 5 divides b minus a. Now that we've shown one direction, we have to show the other direction. So now we're going to say, suppose that a is congruent to b mod 2 and a is congruent to b mod 5. I have to show that a is congruent to b mod 10. Now I'm going to do this very similar to last time. And so because a is congruent to b, what that means is that 2 divides b minus a, and 5 divides b minus a, because a is congruent to b mod 5. And I have to show that 10 divides b minus a. So, therefore, b minus a is 2k1, and b minus a is 5k2, and we have to show that b minus a is 10k3. Now, in this one, the last one I was able to factor, this one I'm not going to be able to factor, so I'm going to go back to some of my other examples to realize that, oh, well, 2 divides b minus a, so 2 divides 5 times k2, therefore it divides the product, so it has to divide k2 since 5 is odd. So what I get is 2 divides 5k2, so 2 divides k2, so k2 is equal to 2k4. Now I can use this to get what I'm looking for, because b minus a is then 5 times 2k4, which is 10k4. And so we'll just let k3 be k4. And so what we get is b minus a is 10 times some integer. Therefore, 10 divides b minus a. Again, that goes back to the trick that we've been kind of using again and again, is that since 2 divides it, I can write this one as divisible by 2. So I can then put it together to get out the product I'm looking for. So I've shown both directions now. So this if and only if statement is indeed true. For our last homework problem, we want to do an existence proof. That is, we want to find an x that satisfies the given properties. And that is, we want to find an x such that n is both an element of x and n is a subset of x. Well, in order to do this, I'm just going to start saying, well, what should x look like? Well, if I list the elements out, n has to be in there because I want n to be an element. Also, though, I want n to be a subset of x, so everything in n has to be an x. So I just have to put in 1, 2, 3, 4, 5, dot, 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 and all the natural numbers. So what do I end up with in this case is the set consisting of the natural numbers as well as 1, 2, 3, 4, 5, or all the natural numbers. And so notice I've constructed a set which n is an element and a subset. So that is my entire proof. I found the set. That's an existence proof. I am done.